Um, so, vu que c'est souhaité, on pense nous commencer. So, good evening, everyone. Welcome to our second session for our webinar, our workshop on AI and certification. Okay, it's really an absolute joy to have you here. Hope that you already had dinner because we'll be ending well past 8 o'clock. And well, for today, our host will be Mr. Darrell, a year one student actually. And I always encourage the year one to voice out, to come and take the stage, because this will greatly actually increase, like upgrade your skills, your presentation skills. And even if you have this little fear of talking in public, well, online is actually a really good platform to start, because you can see no one and you're talking to 127 participants. So the stage is yours, Mr. Darrell.
Thank you, Yashil. Good evening, everybody. Welcome to a second session of our workshop on the introduction to AI and its application. I am Darrell Matthew Noisette, Vice Course Representative of Mechatronics Year 1 and Executive Member of IMECI. I will be your host for today. This event has been made possible due to the collaboration of all engineering society and of our faculty representative, Yashil Anoop. Before we start, I would like to yield the floor to Ms. Deepshika, chairperson of IMECI. She will give us an insight about IMECI UM Student Chamber.
Thank you, Darrell. Good evening, everyone. I would like to share my screen. Just a minute. Yes. So, yes, good evening, everyone. I am Deepshika Bukal, a level 3 mechatronics engineering student and president of IMECI Students Chapter. Today, I will be giving you an insight about IMECI. We are and what we do. So, IMECI is actually a prestigious institution based in the UK. It was founded by George Stephenson, also known as the father of railway. These are some of honorary fellows of IMECI. IMECI is actually headquartered in the UK, and we have around 120,000 members all across the globe, and Mauritius has some members, and we represent the Middle East and African countries. IMECI has several divisions, almost 10, as you can see on the screen. And who we are now. IMECI Students Chapter is a group of mechanical and mechatronics engineering students. We represent the Middle East and African countries. It was founded in 2016, and University of Mauritius is the only university who has an IMECI Students Chapter, actually. We are here for you, students, to organize events and different engineering activities. Now, why IMECI? Because it is a prestigious society in the university. We are here. Why do we organize such events and activities? For you to unleash your talent, to help you build yourself to be a better engineer, to focus a bit on your professional grooming, that is, and to develop and polish some technical and non-technical skills. Now, when you are an IMECI member, you have several events, not only at our level, but only on international level. IMECI provides countless of competitions and events for their members to participate, and it is open. Actually, they do not it is international. I mean, we do not have to be specifically in UK to participate in those events. And likewise, when we participate, we are awarded with prizes. In the events, we have networking. And the most important thing about IMECI is the library. For us students, we are here in Mauritius, but we cannot have access to the headquarters, but we have access to IMECI's site, that is imeki.org, where they post all their research, their journal, their report, by engineers across the world, and they enable us to have access to all of that on the site, and not only on the site, but also on their library. The library has countless of journals, reports, books, ebooks that we can download, we can loan, and also we can have access to sites like Science Direct. They have a report, and they have some reports that researchers actually post, and we do not usually have access unless we are from an institution. And IMECI provides, Science Direct is just an example. We have countless others. And then you have database, access engineering, all those digital resources that will help us throughout our studies in engineering. Also, eBook Central, Kenovel, countless facilities. Now, in terms of events, what we are trying to bring here. Recently, we have not been able to focus about events, about face-to-face events due to the COVID pandemic. But luckily, from this year, we are free to, because it is we are back to normal, no more COVID restrictions as such. So we will be coming up with more events. We are planning site visits. Actually, we already started with site visits last week. We brought mechanical engineering year 3 students to a thermal power plant. We will be having our Speak Out for Engineering competition, the SOFI competition. It is an annual competition in which students have to do a presentation about a mechanical or mechatronics engineering topic or project to a general audience, and they usually have non-engineering background. So when you participate in such events, you have the opportunity to grow in terms of presentation skills, communication skills, and your body language. These are the important things that we should be having as engineers, because we might have the brain, we might have the intelligence, but without expressing ourselves, we will not be able to bring the best of ourselves in this world, in the world that is awaiting us. And we also have the webinar hub that we already started in collaboration with all engineering societies. We did the circular economy previously. Now we are doing the AI webinar, and we will not stop here. There will be more to come. And we are planning also to focus a bit more about health and safety on site, especially because engineers have to be on site. In the future, we will be exposed to many dangers on site. So first aid and OSHA webinar that we did previously, we are planning such trainings in the future. This is a bit of what's awaiting, and these are an extract of the previous Speak Out for Engineering competition that was organized. Networking was really great. Thank you, everyone. This is it from my side. Darrell, you may now have the floor.
Thank you, Deepshika. We hope more students will join us soon. In the last session, we discussed about the application areas of AI, the neural network and Burman logic. In today's session, we will venture into perceptron, understanding a single neuron as the basic of intelligence. We will also use Excel to train neurons, and lastly, we will learn about the multi-layer perceptron and other neural network. I would request our audience to keep a pen and a paper nearby to jot down the main points. Our speaker is Dr. Guruchan. Dr. Mahendra Guruchan worked as a senior lecturer in the Mechanical and Production Engineering Department of the University of Mauritius. He is a chartered engineer registered with the Engineering Council of UK. His accomplishments and work are inspirational and impressive. Dr. Guruchan, the floor is yours.
Thank you very much, Darrell. Just one information to you. Actually, my laptop screen is doing there's some problem there. So you might see me not looking at you because I have another screen. So you might see this a bit strange. I apologize for that. Yep. So I'm just sharing my screen and let's get started. Like Darrell mentioned, so today I'm going to start focusing more on neurons. Like remember in the past session, we did discuss about machine learning, and I've shown the taxonomy really, what is AI, what is machine learning, and where deep learning fits into all that. So my focus now will be more on deep learning, on artificial neural networks. This is basically what I also teach in level 4 for mechatronics students. So this is like a summary of that. So if there were students from mechanical level 4, which I'm currently doing that module currently with them, so you will of course find things which are common with your module, because this is where I take this content from. The objective, like we've discussed earlier with the faculty rep, is to give this understanding to everyone. So in the future, if anyone talks about AI to you or deep learning or artificial neural networks, you have at least some background there to understand what they're talking about. And if this is interesting for you, AI, like we said, is relevant for everyone, whatever field you are working in, economics, finance, agriculture, everyone. So if that is something which you are passionate about, this definitely would fit into your career prospect in the future, so you can deepen your understanding. So it is hope for the 3 parts that we are running gives you a firm background for you to build up and then to read things from the web and to do your self-development. Yeah, so I'm just going to share my screen and we get started with today's session, which is, like Darrell mentioned, more about understanding one neuron. This is what the perceptron is about. Once you understand how one neuron can be modeled in a computer, then the future, whatever neural network you would find would actually be based on that. Of course, you have different theory or mathematical formulations would come forward, but whatever you learn today is very interesting and very insightful for you to extend your understanding now to understand other types of neural networks. So let me get started on that. So as usual, I like to invite your feedback normally. So basically what we've covered so far in the last session, I hope you've got a good indication of where AI is going and what sort of applications you can develop. So just out of curiosity, based on what we discussed last time, and your understanding, maybe you've read in articles now, you can better understand the field of AI. So I would just want to invite quickly your feedback based on what we've covered last time. Have anything come up where you think AI can be applied, or what is a field of interest for you, or any project you're working on currently where you think AI can be applied based on what we discussed last time. So very briefly, like as usual, I'm just going to give this link in the post and just invite some feedback from you. Like it's like a sharing session, you are all sharing together and sort of getting some indication where AI could be applied. So let's quickly look at that. So like it's a Mentimeter again, or you can scan this QR code with your mobile phone, and then we can just invite some feedback from you. I'm just going to share the screen now of your inputs as you do that. So basically, where do you think you can apply AI based on what we've covered already, and any new ideas came up based on what we covered already, or where you think you can apply AI, any projects that you are working currently, where you think you could apply AI based on, like we said earlier, if you've got any data normally, because AI would need past data. So anything which came up during the last session and today we are speaking. Yeah. If you get any problem to access the sheet, let me know. Yeah. So one I can see is home automation in agriculture to produce quality products in the medical field. Yeah. So medical field, I've talked some examples already. If you just Google and if you just see how AI has been applied in the medical field, it's very vast. It's used for diagnosis. It's used by doctors to assist doctors. It's used in many possible. Yeah.
Sorry to interrupt you. We can't see the screen.
You can't see the screen. Yeah, let me just do that again. Sharing it. Sorry for that. Now can you see it?
Yes.
Yeah,
it's
okay, sorry for that. Yeah, I think sometimes the PowerPoint does some issues. So I can see 4 already. So agriculture and farming. So maybe during the Q&A, we can maybe expand on that a bit more. If we say agriculture and farming, so where specifically would you want to use for agriculture? If I can give some examples, in agriculture, it is used in autonomous system to detect, for example, if you have, let's say, pesticide, or if you have an automated system where you want to spray pesticide, you could detect where are the weeds and where you don't have weeds. So you could use that AI for that. I've also seen applications in AI for detecting plant species. You know, in agriculture, people who are in biodiversity, it's important to know what plant species we're dealing with. And this can be quite difficult to do for a non-expert to go around and then to see which plant species we're dealing with. AI can help in that. If you just give images of a plant, for example, it can tell you what species it is. Self-driving car I can find here. Yes, there's big scope for that to detect the environment and to detect many inputs for sensor fusion. Yeah, in the medical field, I've said games develop. So games use a lot of AI. That's sure, for sure. More realistic online activities such as shopping or gaming. Yep, that's correct. Even in learning now, AI systems are being used a lot to enhance the learning experience of students based on the sort of, let's say we ask students to answer some questions, and based on the answers, you can already do profiling based on AI algorithms to decide what are the strengths and weaknesses of that learner, and then you can direct that learner to specific content. That is also very interesting. I can see one, advanced medical facilities. Yes, electronics to create smarter devices and maximize the functionality. We know the field of IoT is a very promising area now, and IoT allows you to collect loads of data. There's no limitation as such in terms of cabling, so people in electronics will do that. So once you have data, it means you have opportunity to apply AI to understand your process, and in real time now to use this IoT data to predict the system performance and to optimize it. Yeah. So lots of opportunities. I can see someone saying accounting. So I'm not really from the field of accounting, but if you have any data which allows you to track maybe data integrity or to do predictions, we have one example to do prediction of house prices. Maybe it is in that area. You can use AI, like I've said last week, in stock prediction. So stock, we know, is a very important area for finance, for stock markets. So if you can predict it as accurate as possible, you can make very astute, I would say, very intelligent decisions, which can make you lots of profits. So AI is also used in these areas. Yep, so thank you very much, students, for this. So as you can see, and I would expect as you cover today's session and as well next session, maybe you have a more open mind now and you're able to identify really where AI fits in and what sort of projects you could work on which can benefit from AI. That's the whole purpose. So thank you for that. Now I'll just be stopping the sharing and let's get into the slides now. So as usual, if you've got any question, you can post a question and we can take them later. Now let's move on. What I'm going to show next, you remember there was we mentioned last week that there was a big debate on what is intelligence and what's the debates going on. And I did mention to you, you can get these answers actually from your own scriptures and by digging more deeply into your own background and your family, maybe discussing with family members. So I just want to share you a few of the quotes I have from my own background. So I would encourage you also to bring this forward, to have an open discussion with your friends. These are some excerpts I've seen from my own background, from my own scripture, which mentions about the debate going on in the field of AI. Like I mentioned to you, modern science is struggling to find these answers, but the answers is not in the realm of modern science, unfortunately. Yep. So if you find these, just some extracts there, which deals with exactly what we're dealing with. Are we fully physical or do you have a non-physical aspect? We did invite some answers last time, which was quite inspiring for me. So I'm sharing you some of them. If you just see the terms highlighted there in blue, if you just read quickly for that. I myself have read many scriptures from other religious backgrounds, like the Bible, the Quran. So I'm very happy to read these things and I find lots of commonalities. So what I'm sharing to you here clearly shows, yes, there are things that are discussed in our scriptures, which will be very useful in this venture understanding ourselves, and some more here. If I just read the first one, it's very interesting. It's talking about our senses, our eyes, our tactile sensing, our nose, our ears. So it's saying here our senses are superior to dull matter. It talks about the mind being higher than the senses, intelligence still higher than the mind, and it talks about the soul in all this. So I think if you get this type of very precise information about our existence. It really opens new scope for understanding this, as opposed to just relying on science to try to test things with instruments we're creating, and we might not end anywhere. Yeah, just some extracts, but I would invite all of you to have a very, I would say, very open discussion among yourself. If there are things you find along the debate going on the field of AI which can enlighten each one, I would encourage you to do that. That's just a sort of a parenthesis. Now, like I said to you, let's start with a very simple example of a prediction example. You would have all done linear regression in HSC or SC. So I would want just to show you where are we trying to go with AI. Yep. So we just want to just use some data and just do some prediction. And then I will show you how come we are limited if we just use very fundamental mathematics and where AI can bring us forward. Yep. So you would have used mathematical tools like regression. If I give a table like this, for example, to you, where let's say we want to predict the price of house based on the area that a house is. Normally, we'd expect as the area grows, a house price, of course, is going to grow. So what I'm going to do very quickly, I'm just going to copy this data and put it in Excel. Just do a quick analysis for you and just show you what sort of, like I said, the host mentioned earlier, we'll be doing some analysis later in Excel. Yeah, so I'm just going to paste data here. So once you paste that here, you know you can just do a very quick scatter plot. I hope you can see the Excel sheet. If there's any problem, let me know. I'm trying to share the whole screen. Yep, so you can do a quick scatter plot as follows. You would have done that in your modules. I'm getting some problem because on top we have this bar there, which hides the menu. So if we insert a simple scatter plot, you get something like this. So I hope you can all see the scatter plot, which I've just put. So very simple points there. On the x-axis there, you have the area of a house. And these are some arbitrary data I've taken. Yep. So you can very easily just do a scatter plot. But what you can do next, of course, you can start doing a line of best fit. So in Excel, that's quite easy to do. Students in class here who are doing programming with me would be familiar with what I'm doing if they're doing programming in mechanical engineering with me. So you can clearly show the equation, and normally we have an R value you can give to actually give some information about the fitness. Yep. Is it a close fit or you have some errors? As you can see, the R value is close to 1. So you conclude it's a quite good mathematical model. Yep. So now interesting here, once you get this model, what can you do next? You can now use this model to do prediction. This is where we're coming with this. So very simple exercise, I've just taken the data, put the scatter plot, and just fitted a line of best fit there. So you can easily do that in Excel. Yep. So question for us now is, yep, once you get this line, what can you do with it? Of course, you can now use this to do prediction. In the future, if you get a house and you know the area, you can use that simple mathematical model to predict. This is where AI also is a very core objective of AI, is to be able to build a mathematical model or a learning engine, which you can use to predict now in the future if there are some factors which are there, like the stock market, for example. If you know there are some factors affecting the price of stock, you can now use these factors to predict how the stock or the currency rates will change. That is a very useful example for finance people. Now, what I've just shown to you is this example here. You had one independent variable called area. Yep. And the target output was price. So very simple, like a y is equal to mx plus c could get a variable. Now, imagine the price depends on the location, the type of finish of a house, whether there's a swimming pool or not. So what I mean here, as you start complicating the problem more and more, yep, if you start complicating the problem more and more, it becomes difficult to show that graphically. Yep. The one I've just shown to you was actually a very simple problem, just one x-axis and then just y. Now, imagine you have a table you're constructing where you're putting the location in Mauritius, for example. The type of finish would be, is it a high-class finish? Will it be very good tiles and so on? And was it a swimming pool or not? So as you start complicating the problem, and maybe you need to do that to get a good estimate. Let's see one chart there. Yeah. I hope you can see me. So I would request the host, if there's any issue, let me know. Like, I hope you can see the screen. So what I mean there, as you start complicating the problem, having more and more factors, it's no more possible to just draw that simply. For the simple reason, we human beings and the way computers graphics are, we can't plot beyond 3D. You can do a 2D plot like you have just seen. If you have two independent variables, you can have a 3D plot. You have a surface. That should be also okay. But the moment I have three independent variables, you can no more plot that, and it start becoming difficult. So this is where we'll be seeing how neural networks would help us as we go along. I don't say it is impossible to do mathematically. You do have multiple regression. You can do that, especially from the field of data science, like we told last time. But for someone who's not advanced in mathematical tools, it becomes difficult. So as we'll be seeing today, neural network can be of interest for different people from an application perspective. If you're not interested in the algorithms, you can just use neural networks to just quickly train a problem and use it. You could also be a developer. You are developing the algorithm. So it's really for everyone to contribute. Now, the video which we've seen last time, I won't show it again. I think you did receive the links, and this was a very important video which showed you actually how the human brain works, and the topic there is neurons. So basically now I'm just going to quickly revisit what we've seen last time and what were the main findings in that video to help us to create an artificial model for the neural network. Yep. Remember, our brain is basically based on chemistry, on electrochemical reactions. So that's what we saw in the video, how our neurons actually activate. If you see the video, it is based on electrochemical reaction with transmitters and receptors and so on. So what are we trying to do now? We're trying to get these findings and try to create a model, a mathematical model for the neuron, for one neuron. This is the objective of today. Now, once you do that, then you can start connecting the neurons together, and they would start behaving in a way which is analogous to our to the neurons of our brain, but of course at a much less complex level. Now, some data just quickly there. A neural network is a model of reasoning. So basically, we're talking about intelligence there, and we know intelligence is linked to firing of neurons. Now we're trying to get this why we're interested in how neurons fire, and quite amazing data there. You have 100 billion neurons in our small brain, yeah, and we know that these neurons are connected, and typically you have 60 trillion neurons connections in between them. Now we'll come to this term synapse as we go along. Now, interesting, our brain works in parallel. It's not like each neuron is going to fire sequentially. All these 100 billion neurons can fire at the same time, and it's really impressive how our brain can be really very powerful, and it's much faster than the fastest computer that we know today. So our brain really is a supercomputer, even a hypercomputer, you can say. Now let's go into details to understand how our brain neuron works from a biological perspective, and then we are able to create this mathematical model we're aiming at. I wanted to show this diagram to you. Remember when we look at the video, we had a similar thing like this. We had the neuron, and then the neuron will be having lots of branches like this, which are called dendrites in biological term. And then all neurons would have only one output. That's a very important observation for us. All neurons will have only one output, and this output will actually feed the dendrites themselves. Yeah? For example, you can see here you have one of these axon. This is how we call them. The output is called axon in biological terms. So this axon is going to actually create a potential, an electrical potential, very small voltage, but electrical potential, to actually impact on the dendrites of other neurons. That's how it works. Now, this diagram shows the electrochemical reaction I was talking about. So when you have this electrical potential coming in, it emits molecules, which actually, these molecules travel in a small gap. So it's not physically connected. Your axon and your dendrites are not physically connected. You have a small gap called a synapse. And this synapse is fundamental. As I'm going to talk along, the synapse is a fundamental component of a neuron. And these receptors you find there are actually on the dendrites. Now, dendrites are many. So a neuron can have many number of inputs, but only one output. That's a fundamental observation made on the neurons in our brain. Yeah. And the synapse we talk here is a fundamental component for us because this synapse actually determines how much of these transmitters actually come to the dendrites or to the receptors. If that synapse actually inhibits the transmission, then even if this is firing, it will not cause any effect here. On the other hand, if the synapse actually encourages the transmission of these molecules, then this neuron would have a huge impact on the input. So basically, what this synapse is about, if you think well about that, what I'm going to say, this synapse is actually the seat of intelligence, folks. As you're learning to grow and learning to like I mentioned in the last session, as you're learning to grow and to learn new skills, to run, to walk, or to sing, or to speak a new language, you are actually tuning this synapse. Yeah. That's very powerful, what I've just said. You are actually tuning the synapse, and this is what we'll be doing when you'll be training a neuron down the line. Yeah. Now, this is just a background. You'll be getting the slides. You can read on that. But so we've concluded that in our brain is mostly chemical substances which are transmitted. It's quite impressive. If you read on neuropsychology, you will find that in our brain, you have small pumps and small valves opening and closing. It's very impressive. Yeah, you have good books on that. So I would encourage, if that's of interest to you, you can read about that. We've talked about the synapse, a very important component. Yeah. Some more information which you can read about how our brain is plastic. So, for example, our brain is not just static. When you're learning new things, continuously the synapse is being modified. So you can learn a new skill. Like I mentioned last time to you, you've just seen me. Those who did not see me before, now you've seen me giving this workshop. So now today you're seeing me again, you recognize me. So what happened inside your brain that you are able to recognize me? The synapse have been modified. So these actually quite, I would say, quite revealing how actually our brain is working. And for most of us, I would say we are not aware of that. That's another irony, I would say. We don't even know how our own body works and how for example, our heart pumps blood and how it is beating. And there are so many things in our own body which we don't understand, but still we are living and we are quite good in our field. You're all students, you're learning well, but there's so many processes in your body which we don't master. Yeah, so it's very important to understand this. And based on the findings from your science, like we are trying to aim now is to try to create that model, which would allow us, of course, to understand us a bit better, but unfortunately not enough so far to understand really what's happening inside our head. Okay, so information is stored and processed in your network simultaneously throughout the whole network. Like I mentioned earlier, it's a very powerful process going on in our head. Yep, and so the processing is not just local, it's global. Yep. I've talked about that. The neural network learns from experience by strengthening connection between neurons leading to the right answer and weakening those leading to the wrong answer. So what are we trying to say here? Let's say when you're growing up as a kid, let's say your parents will say, don't say bad words at home. Yep. So every time you say bad words, your parents say, don't say this, don't say this. So inside your brain, what's happening? You are being tuned to say, yes, this is a wrong thing. So your brain is really, so for the right answer, which you are being motivated, this is going to reinforce some connections in your brain, and the bad one, which your environment is saying this is wrong, then this is going to sort of weaken this sort of response. Similarly, when you're learning how to walk as a baby, when you're growing up, when you will do some gates, for example, you're trying to do some steps. If you do the wrong step, you'll fall down. Then you know, yes, I've done a wrong step here. Yes, I don't need to do it again. So inside your brain, what happens? Inside your motor part, inside your brain, some connections are being reinforced and some weakened. So over time, you become very good at walking, then you would never fall. Same thing with running. So this is quite, I would say, insightful if you understand really how all this works. And really, we are using all these findings to create neural network, which can give us right and wrong answers, like we say, classification type problems. This is how a mathematical neural network look like. So you have many inputs coming in, and then you have some output, which is going to be generated for us. But you do have these middle layers. So what you find here is an artificial neural network, because this is nowhere close to what we have in our brain. Because when you look at our brain, all are so connected together. One neuron can influence so many of the neurons. It is not as simple as that. But the good thing is, even with such a simplistic neural network, we have been able to do fantastic work, where you can define the inputs here. For example, I mentioned earlier, this could be the area of the house. This one could be the, do you have a swimming pool or not? This could be the type of finish. This could be the location. And the output could be just one neuron, or it can be many number of outputs. Now, the middle layer there, it is normally called a hidden layer, because these layers, actually, their output is hidden. You're not interested in these outputs normally, but they are important for you to be able to create a final output. They are intermediate states as such. Yep. So basically, when you get an input, the input is propagated forward. This is what we understand one neuron today, how one neuron can be modeled mathematically, so that when you get an input, you can propagate it forward and get an output. And when you mentioned, remember we mentioned about the synapse. The synapse are just arrows here. So these arrows will be given some weights. If the weight is 0, means this input is not influencing this neuron at all. This is what I mentioned about the synapse. If this input is given, the weight of this arrow is given a negative value. So this weight there is penalizing this neuron. If it's given a positive weight, it's going to enhance this neuron. So this is how, by just putting a simple weight there, you are able now to decide the influence of one input on the other input, on the other neuron. Same. So this neuron is trying to influence this neuron, but it depends on the weight here. So what is intelligence in a neural network? Basically, it is the weights of these different arrows. When we learn how to do training, we actually will be adjusting these weights so that when you feed a given input, you get the output you want. As long as you don't get what you want, you'll keep modifying these weights. This is basically what you'll be doing down the line. So this is what you'll be doing today, trying to does a weight justify the priority of input? So we're going to discuss that as we go along. Yep. So maybe this becomes clear. Yep. So the weights basically is a synapse, like we said. What we have in our brain is actually a gap. Yeah, we have a gap, but in an artificial neural network or in a computer system or on paper, as we're trying to develop a mathematical model for the artificial neural network, this is going to be represented as an arrow like this. Now, one fundamental thing as we go along, yeah. So I think this you can read, and I've talked about that the neural network you're creating are very simple compared to what we have in our brain. So you can read about that. Some areas of application, you can read about that also, where it's being used, that's okay. Now, we mentioned about that each neuron produces only one output signal. So it's always a case, one neuron would always have one output, but yeah, as you can see here, this neuron, even if it is shown that this output is many, actually the output is only one, but it is split into different. So if that is one output, then you can imagine the output is being split into many to feed other neurons. But it is just one output. Each neuron has only one output. That's a fundamental observation. But one neuron can accept a number of inputs. Like this neuron here can take 2 inputs, as you can see, whereas this neuron here can take 4 inputs. Yep. Yeah, 1, 2, 3, 4. Yep. So this is a fundamental observation from our own brain that one neuron can take many inputs, but can output only one, can produce only one output. Although this one output could be distributed to other neurons. So I mentioned about the numerical weight. The synapse I mentioned about would now be mathematically modeled as just a simple weight, and we will adjust this weight as we do training. We're going to see that. So a neural network learns by repeated adjustment of its weight. This is how you also learn, by modifying your synapse. Now, also, if you understood this concept of a synapse and electrochemical reaction, you can also understand what influence drugs and chemical substances have on our brain to create illusion or hypnosis and so on. So basically, you are creating a situation where this synapse is really being controlled by chemicals. So this is how you understand it as well. Now, based on inputs and numerical weights, each neuron can compute its activation level. So this term is very important. Remember when we looked at a neuron, we had something called a firing of a neuron. If you look at the video, you'll find like a lightning going out. We've seen that in the earlier diagram as well. This is called activation. So the activation basically is a function. Yep. Now, this diagram is simply showing the analogy between the biology. So the soma is called neuron. This is biological one on the left, and on the right is what the term will be using. We are more accustomed to input as opposed to dendrite, and the axon is going to be called an output, and the synapse will be called a weight now. So now we're going to transit into a mathematical model. Yep. So we will show in network architecture basically is how your neurons are connected, and we'll also develop today a learning algorithm to train the perceptron, which is just one neuron. So we'll start with a simple one, but like I say, once you get that clear, you can build up that. This is one neuron, how it is represented. So this neuron has 3 inputs, x1, x2, x3, but it's typical that one neuron can have thousands of inputs. From the application I've shown you on the first day where I want to detect the eye corner, imagine one of this image, which I had where the eye corner is located, is let's say a pixel, let's say 30 by 30. Very simple sub-image. 30 times 30 is 900 already. So it means you have already 900 inputs, which was going to be fed to one neuron to tell me, is it an eye corner or not? So here I'm just showing a simple example with 3 inputs, but it's typical that the dimensionality of your input is very high. Now, for every input, you need to have a weight, as we've seen. So for x1, we're calling it W1, x2, W2, x3, W3. So every of these input, we have a weight, which is feeding into a neuron. And from these inputs and the weight, we need to find a way to find the output Y. Like I mentioned, the output Y is just one, but it could be distributed like this to other dendrites. But this is why it is not Y over 3, Y over 3, Y over 3. No, the same potential, electrical potential is distributed equally to all the dendrites out. That's important to understand. Okay, now this brings us to a very important calculation we have to look at is something called a weighted sum. Yep. So if you look at this diagram earlier, we have x1w1, x2w2, x3w3, and we can have xnwn. So we have many inputs with the respective weights. So we have to do a simple weighted sum. So what we'll do, we'll take x1 times w1, x2 w2. So we're going to do a multiplication, add all of this together. Then we're going to get a capital X. So capital X is simply you just do the weighted sum of each input with the respective weights. That's very simple. So you take x1 w1 plus x2 w2 plus x3 w3. You will get capital X. So this is what this is mentioned here. So for any neuron, you will do a weighted sum of input, and then you will compare it with a value called the threshold. If you exceed the threshold, the neuron would fire. If you don't exceed it, the neuron will not fire. It's a simplistic activation function. I will show you other activation function as we go along. Yep. So the simple one is you just do a weighted sum, like I mentioned, W1, X1 W1, X2 W2, X3 W3. If you have X4, you do X4 W4, and so on. All this sum would give you capital X. So capital X is equal to this weighted sum. Then you will compare capital X with the threshold theta. If your capital X is greater than theta, your output will be given a value of 1 that's high. And if it is not, then you give a value of 0 or -1. So basically you are saying 1, the neuron is firing, and 0 or -1, the neuron is not firing. This is the most simple one I can show you. You would know about the step signal. Those who are doing mathematics, or you're doing signal and system, or any module, or in the future you would do it. This is exactly what I've just described to you. This is your capital X here, which is the weighted sum of all inputs. So now you know how to convert to individual input with the respective weights and get a capital X. That's very important. We'll use that in Excel as we go along. Now, this diagram, this function, step function, is called an activation function because this is mapping your input onto an output. Basically, seeing here, it is saying if capital X is more than 0, your neuron fires. If it is less than 0, it doesn't fire. This is one way you could represent it. Yeah. But remember we mentioned about theta. So in this graph there, theta is 0 because this is where theta is. If you start playing with theta, this graph will shift left and right. I'll just illustrate that quickly for you. Yeah, in Excel. How can you play with theta? So again, I hope you can see my screen. So we just mentioned earlier your capital X. Yep. Remember your capital X was a weighted sum. So if you have many inputs and many weights, you can always calculate capital X. Yep. Now from capital X, let's say I want to generate the step signal. Our step signal, very simple. Yep. So let's take just some arbitrary values. Let's say from -5, and I'll just take some is equal to, just create a domain. Let's take a couple of values here up to +5. Yep. And to create a step signal, as you've just seen here, it is not possible to have a mathematical equation like in terms of y and x because it's piecewise linear. So you have a function in Excel called if, which you can use if you. Yep. So we can do that. So basically, it's going to be like this: if your input, as you've seen, is greater than or equal to 0, then it's a 1, else it's a 0. This is what the step function does. Yep. So if I just populate that, you will see when x is 0, it becomes 1, and when it is 1, it have a step there. So like we've done earlier, I can just create a very quick scatter plot. If you can't see the screen, let me know. So this is a very quick scatter plot of, as you can see, the step there. Yep. It's a step signal. Now, in this formulation, they have not included theta. Theta is 0 here anyway. Yeah, but normally I will have a parameter called theta. So let me just define in that sheet itself theta for you to see it. So I'm creating here a variable called theta. And the value currently I'm putting is a value of 0. So currently theta is 0. Okay. So in the formulation now, I need to always compare my capital X with theta. So I'm subtracting theta here. Yep. So basically I'm saying here x minus theta. If it is positive, then it is 1. If it is not positive, it becomes 0. So currently you will not see any change because theta is 0. So you see what we get. But if I go back to the name manager, I change the value now of theta to, let's say, 2. Let's see what happens. Yeah. Have you seen the graph has shifted to right? Earlier the threshold was here. When I made theta become 2, now the threshold is here. Yep. If now I'll just make one more change just to show that to you. If I make theta equal to -2, so because I'm comparing theta Have you seen how shifted now to left? So basically, theta's role is to shift the whole activation function left to right. This is what theta does. Yep. So just bear that in mind. Yep. So let's continue. We've just shown to you, but in this graph you find there theta is 0. But if I start comparing your capital X with theta, let's say theta is 1, then this step would come here. If theta is -1, the step would come here. Basically, by changing theta, you are changing the activation of the neuron. You're deciding when the neuron fires and when not. So this is quite powerful. Now, very similar to step function, you can have a sine function. Instead of it being 1 and 0, it can be 1 or -1. So 1 can mean accept something, and -1 can mean reject something. So in the graph I've just shown you here, if you go back to Excel, if you want to do the sine, very simple. I'm just going to say -1 here. So instead of 0, I put -1. And if I double click there, instead of this one, you get -1. So now the graph is going to -1. Nothing new here. And as I've said earlier, same thing. If I just do that one more time for you to see, if I change the value of theta back to 0, yep, you can see the whole graph now is centered on 0. So again, theta, irrespective of activation function, shifts your whole activation function left or right. That's the purpose of theta. Now, a few more activation functions. Now, what activation function is, just a quick recap on that. Basically, activation function, take your capital X there, which is your weighted sum of your inputs. If I just go back again, this is your neuron there. I just do that capital one more time for you to see. If I change the value plus X2W2 plus X3W3, so you can agglomerate, accumulate all your inputs and your weights to get a capital X. You compare your capital X against your threshold. If it is more than 0, then you have either 1. If it is less than 0, then it is 1 or 0 or -1. This is what you see. Yep. This is the step and the sign. Now you can have activation function like this now, which is called sigmoid. Yep. So sigmoid activation function, as you can see, is not step. Yeah. If you look at these two, it's just a step signal. So the gradient here is 0, gradient here is 0, gradient here is infinity. So you can use this type of activation function for classification. Let's say you want to say this is an apple, this is not an apple. That's fine. But if you have any application where you want to have a continuous output, then you can't use the step or the sign. You would need to use continuous activation functions like this. This is called sigmoid. Yep. So you have an equation for it. Yep. I will not. It's not important for me to give it to you today. You can Google it. Yeah. It's actually 1/1 plus exponential minus x. Similarly, there, this graph is shown for theta 0. This is why you find it centered here. If I make theta become 1, you find the whole graph shift to the right by 1. And if I make it -1, it shifts to the left by -1. Same thing like you've seen earlier. Now, this activation function is used actually not as part of Perceptron, but for more advanced neural network. This is called sigmoid. Yep, just to give you that information. This one is very simple, the linear one, so y is equal to x. This is also used a lot in modeling for mathematical people. Mathematicians will use that a lot to use neural network to do approximation of mathematical functions. So you use y is equal to x. So this one's pretty simple. So y is equal to x. If you, let's say you have a value of 1 for x, your y will simply be y itself will be 1. So very simple. Whereas this one, let's say you have a value of 2 for capital X, then you're just going to use the equation and you will get the corresponding value here for your activation level of your neuron. So again, your activation function allows you to map your capital X onto the output of the neuron. This is what the activation function does. Yeah. So we've talked about that already. Yep. So let's start with a perceptron now. Yep. So this is one of the simplest neural networks you can have, but yet very powerful. It's called a perceptron. So perceptron is just one neuron. And in this one, I'm just showing two inputs, X1 and X2. Yep. But you could have X3, X4 as we've seen. Important is every input needs to have only one corresponding output. Sorry, one corresponding weight. So I just want to shift here. Yeah, sorry. Yep. So each input needs to have a corresponding weight. So X1 you have W1, X2 W2, and the neuron would have a threshold theta. Remember, I've talked about theta already. When you get to capital X from X1 W1, X2 W2, yep, you have to compare or subtract theta from it, and then you apply your activation function. This is important. So if I show the steps now to you in more detail, this is a neuron we had earlier. So you're going to first do an agglomeration. This is accumulated sum. And then you will subtract theta and then apply the activation function. So inside this neuron here, you have these fundamental operations, mathematical operations you're doing accumulated sum of X1 W1, X2 W2, add all of them. and then compare with theta, basically subtract theta, and then apply in the activation function, be it step, sine, sigmoid, or linear, or there are a whole range of other activation function to calculate capital X. So this is how now you can start activating one neuron. And remember, all these operations we're doing stem from neuroscience, how our neurons have been found to behave, and we are trying to replicate that mathematically. Now, to show you a bit in more detail now what the perceptron basically is doing. In this neuron here, you can find you have two inputs, X1, X2, and you're producing an output of Y. Yep. So if you use a simple perceptron, the perceptron is creating a line like this for you. So it is of a form Y is going to mx plus C. Yep. As we've seen, X1, W1, X2, W2 is your capital X. You subtract theta. Yep. And this gives you the line of this, the equation of this line. Everything above this line would be classified as class 1 and below it as class 2. For example, class 1 can give a value of 1 in a step activation function, and class 2 could give 0. In a sine activation function, this could be 1 and this could be minus 1. But important is that neuron, that perceptron is putting that line for you. We understand that in a few minutes, how this works. So if you have X1, X2, you will get a graph like this. If you have X1, X2, X3, like this one, where you have X1, X2, X3, but still one neuron only, you will do the same calculation. You will take X1 times W1, X2, W2, X3, W3, cumulate them, subtract theta, fit activation function, you get capital Y. Now, what sort of geometry you're getting now? You're getting a plane. This is showing a triangle here, but this is actually a plane where everything above the plane will be class 1 and everything below that plane will be class 2, just like this. So this is in 2D, this is in 3D. Now, if you had a neuron with 4 inputs where you have X1, W1, X2, W2, X3, W3, X4, W4, you would also get a hyperplane, but it's not possible for us in our world, at least, to plot it because we can't plot beyond 3D, unfortunately. But it is still possible to imagine how that hyperplane would look like. It's going to have a term plus X4, W4 minus theta equals to 0. This is the geometry which is created by one neuron. It cannot create a geometry which is not linear. So this is one of the limitations. We'll see that as we go along. To illustrate this perceptron, remember I've shown you toward the end of the first session, I've shown you the Boolean expression, the AND gate, the OR gate, and the XOR. I would illustrate this now in a few minutes to show you how we can imagine this, how the perceptron is working. Let's look at the first one. Now, what I've done here, if you look at the logical AND, if I just do that quickly in Excel, that would be useful for you. I'll just do that quickly in Excel for you. And then we'll come back to this one, you understand it better. Yeah, let me just delete here, this one. Yeah, okay. So I'm just going to paste this table there. So as you can see, I have two inputs, X1, X2, and we're having an AND. So what I'm trying to do here, I'm trying to create a scatter plot where I can show all the, so this is class 0 and this is class 1. This is what I mean by classification. So basically this can be imagined to be one class and this can be a second class. Similarly, in the operation, this is one class and this is a second class. Yep. And similarly in the XOR, you have these two are one class and these two is another class. How I can show these classes on a scatter plot is quite simple. I can highlight all the combinations of input corresponding to class 0 and I can insert a scatter plot. As you can see, these 3 dots there. So these 3 dots which you find, they correspond to grade to class 0, as you can see. Now, if on this same graph, I add, so I can call this one class 0. Yep, so this is done. I can add another class now because I have this class 1 here. I can add class 1 and the input X is this one and the output is this one. So as you can see here on this scatter plot, these 3 dots, the blue ones correspond to class 0, so this 3, and the orange dot here correspond to class 1. These are a very simple classification problem. I will bring to one more complex one. I can hear some background. Sorry. I can get some background noise. Maybe some students need to just mute the microphone. Thank you. Yep. So what you can see there is a very simple graphical illustration of the classes. So these 3 dots there, the blue one correspond to class 0, and this one correspond to class 1. So similarly, now if I can shift to the slides just to show you what result you will get. So this is what I've just shown to you for the N. Yep. So these ones are your class 0, and this is your class 1. Yep. And this is what the perceptron would do. The perceptron is going to put a line in between this here to separate your class 1 from your class 0. Now, when would this line be here is when your weights are right. Remember, these weights are fundamental in setting this boundary. As I change W1, W2, and theta, this line would change up and down. I want to choose values of W1, W2, and theta, where this line is sitting exactly between the two, and allow me to give these different classifications. So above that, that's going to be class 1, and below it, class 0. Now, this example is very simple. As you can see here, I've set W1 as port 1, W2 as port 1, and theta as port 2. And it actually gave me exactly this equation by, if you want, you can calculate it by using mathematical methods, or you could do this arbitrarily. But this is just to illustrate how the perceptron works. Ultimately, you want to do that automatically, especially if you get more number of inputs. You can't just draw and then put the line there. But this is basically what the perceptron is doing, is putting that line here for you. Now, if you have a problem, a few minutes I will come to that. So this is for the N. This is for the O. Remember, the O has 3 class 1 and only 1 class 0. If you look at the truth table for O, you'll find you have only 1 0 and you have 3 1s. Yep. So this is how you can draw a simple scatter plot to show where the perceptron is going to put the line. So similarly, W1 is port 1, W port 1, and here theta has changed to 0.1. Then you get this decision boundary. Again, these values have been put there arbitrarily, just to illustrate simply how it works. But down the line, in a few minutes, I will show you how you can create that automatically. Yep. So again, as you can see, for the O function, it's possible for me to draw a line here. It's possible for me to draw this line. Yep. So it means the perceptron is able to work. Now, look at this one now. This is Xor. The Xor operation has 2 class 1. So these are the shaded ones, and 2 class 0. If I just show you the truth table for it, this one here, the Xor, when x1 and x2 are both 0, you have 0. And when both are 1, you also have 0. This is why if you look at the Xor here, when both are 0, you have 0 here, and both are 1, you have a 1, else you have the 1 here and the 1 here. Now the question for you, if you compare this one and this one for the N and the O, where we were able to draw a straight line between the two. For this one, can you think of a straight line which will separate the shaded from unshaded one? Is it possible to draw a straight line that would separate like here? If I draw a straight line, you can find on one side I have all the shaded and on the other side all the unshaded. Yep. Is it possible to draw a line like this for this one? Try to think about that. That's very important. It's called the Xor problem actually. So over time, if you read about the history of neural network, you'll find, yes, there were many type of function, many type of problems which were like this or like this, which could be solved using one neuron, which would classify, even you have hundreds of inputs, but if your classes are separated by one single line or by hyperplane, like I've said in high dimension, then a perceptron is able to classify into different classes 0, 1. But if your problem is of this type where you are not able to draw, so if you want to draw a boundary, maybe it's going to look like this. You can start, if I just shift that to paint, just to illustrate to you, I hope you can see paint. Yep. So this is your x1, x2. So if I try to draw a straight line, I can try to do like this. It's not possible. It's not possible for me to draw one straight line to separate the two. Yep, it's not possible. So maybe I would have to draw something like this. Something like this. No, I need to draw the pen. So maybe something like this would work. This is just one tentative. Something like this could work. Yep. So as you can see, on one side, I have all the shaded and one side all the unshaded. This would be a boundary, one potential boundary. But the fact that this boundary is not a straight line, it means the perceptron is not able to classify this type of problem. This is very important. This is called the Xor problem. Yep. So just to recap on that, it's a very fundamental observation. If you have problems like this or like this, you can solve it with one neuron to classify. But if you have problems like this, called the Xor problem, so people have taken almost 10 years to solve that. Yep. So how to solve that? We need to consider more advanced neural network like the multi-layer perceptron, and the training is much more complex. This is what we'll be doing next week. Now, I'm going to take one example now, which is more complex. Can you tell me, these are very simple data here where I have just 4 combinations and the output is just binary. Let's take this one here. I'm going to just take that and bring it to to Excel again and show you if your inputs were non-linear, were not just binary, you can still do classification. Just give me some time, just paste this here. So as you can see, you can use Excel to do quite a lot of analysis. So I'm just going to paste this data here. Now, this X1, X2 actually continues down. I've just shown them at the side just because we don't have enough space. So I'm just going to take them and cut them down here. Yep. And these are your corresponding classes output Q, which is still binary in this case because we're doing classification here. So 0 and 1. Yep. What I'm going to do next, you can do a very quick sorting. So you get all your zeros and 1 together. As you can see, all your zeros and 1 are nicely together now, and all your 1s. So basically, all this data here for X1, X2 correspond to class 0. So I can highlight all of them. And I can just insert a scatter plot like I've done earlier. So all these blue dots here correspond to class 0. I can go back now and, like we said, this one, if I just edit it, it's class 0. Yeah, so the blue ones are class 0. I can add now a class 1. And let's select the X values. The X values will be here for 1. So these are the X values. It's a 2D plot still, so I can graphically show it. But like I said, if it goes to 4D, you can't do it. Now let's select the Y values for class 1. So these are the Y values. Okay. Okay. Yeah. So now you can see here. So the blue dots actually are your class 0, and the orange one are your class 1. If I just take that into Paint now, yep. As you can see, if I can draw a line like this between the two classes, this problem can be solved by Perceptron. Yep. So like I said, this one is very simple. It's just 2 dimensions. You can do it, but if it goes to high dimensions, then you can't do it. Then you will just try to train if the Perceptron is able to provide the output. Then you can say, yes, it is solvable. If it's not able to converge, you would say it's not possible to train it. But we've seen a few minutes what does convergence means. Yeah, we are coming towards the end here. We don't have too much more to show, but I want to do some training actually in Excel for you. So as we said here, a perceptron is able to, I'll just make it, yeah. So a perceptron is able to represent a classification function only if there is some line or plane that separate the two classes, that is they're linearly separable. As we've seen for the Xor or any problem which you don't have one single linearly separable plane of the form x1, w1, x2, w2, x3, w3, and so on, then you can't have only one perceptron. You have to consider more complex function. Now, by the way, the example I've shown you on the first day for the icon extraction, it was actually sorry, I'm still saying some background noise. Thank you. So, like on the first day, remember I showed you some eye extraction. Remember there was icon extraction and ear traggers. This was done with perceptron. So perceptron is very powerful as long as your classes are linearly separable. That's very important to understand. Now, how do we do this automatically? Remember when I showed you this sort of graphs there, this ones, yep, this one. I've set these weights arbitrarily to 0.1, 0.1, 0.1. What if you have a big data set, and how do you set these weights? So this is what you're trying to attempt now. How can we learn a perceptron automatically? Now, unfortunately, since we don't have enough time, I'm not able to explain this equation in detail with you. Normally in my lectures or workshops I run, I'm able to actually show you where we get that equation from. But I'm going just to explain it to you. But hopefully, if we get any other opportunity, I can go in more detail about that. Now, remember, you have some weights in your neural network, which you will initially set to some random values. Yeah, you will set in some random values, and then you will adjust these weights in some way using some method, so that over time, the output you get from your neuron, if I just show that to you, yeah. Let's say you have a neural network like this, yep. So this output you find here, Y, is coming from your neural network. That's fine. You also have an output which you want to get from your data set. This is your desired output, and you have one output from the neural network, which is what you're getting. And ideally, you want these two outputs to be exactly the same. Then you're happy. You say, yes, I'm getting what I want. It means when you set your weights W1, W2 to some arbitrary random values initially, most likely the output you will get from the neuron would not be what you want. Yep. So whenever you get that difference between your actual value from your neural network and the desired value, you get something called an error. The error is the desired value minus actual value. Then what you would do, you start modifying these weights in a given way so that your actual value from your neural network would be matching your desired output from your training set, and your error becomes 0. So this is what, if you look at the equation I've shown you here, this equation tells you how you need to modify these weights. So this weight should be modified by multiplying the input, because remember, the weight is attached to a given, all your weights are attached to a given input. So if you want to modify a weight for a given input, you multiply that input by the error you're getting. The error, like I said, is simply the difference between your desired value and the actual value you're getting from your neuron. Now, you do have a factor alpha, which is just a fraction, which is called the learning rate, which you would also multiply. Unfortunately, I can't explain to you why you're multiplying these two, but for the time being, I'm just asking you, if you multiply the input X by the error you're getting, you would get actually the sign of how would you change that weight? Is it increase or decrease? You're able to do that just by multiplying your input by the corresponding error. And you would typically multiply this ratio here by this product here by a fraction. That's as simple as that. Yeah. So this is what it is shown here. Remember the delta W I've shown you earlier. This is exactly here. Then of course you will add it to your weight quantity to get the new weight. The equation is simply saying, how do you get a new weight from the old weight and the correction factor you calculated? This actually comes from Rosenblatt, who actually created the perceptron rule. Yeah. So now how you get that correction factor, like I just said, you multiply your input by the error you're getting from the neuron. The error is very simple to calculate. It's the desired value you want to get from your neuron minus the actual value you're getting. Now, I will illustrate that in a few minutes from in Excel. This is what I wanted to show you. Yeah, I'm going to illustrate that in Excel in a few minutes. So we will take the N function itself. Yeah, I'll illustrate the whole step to you in Excel. So this is a training set to be using. Now, what you find here is an N logical function. So you have 0, 0, and then you want to get 0. So when your inputs are 0, 0, you want to get an output of 0. So it's a desired value. So when your input are 0, 1, the desired value is 0. When it's 1, 0, the desired value is 0. And when it's 1, 1, the desired value is 1. So this is a training set here. Now, how you typically do training? Yep, you're going to feed all these 4 data into your neural network, and you'll be adjusting your weights and the threshold iteratively until hopefully the output you will get from your neuron would be corresponding to these ones here. This is what is the desired value. Now, like I mentioned, you'll be feeding that continuously. So this is iteration 1, 2, 3, 4. So you're going to have many iterations. And this is called one epoch. It means you fed your data completely into the neural network once, but you won't have only one epoch. You'll have hundreds or thousands of epochs. So you're going to feed this data continuously into your network. Every time you'll be checking your error. And based on your error and this equation I've shown you earlier, yep, you will have an error. You will use error and the input that you are looking at, and you would modify the weight accordingly. So let's see how this works. Yep, let's see that how it works in an Excel sheet. So I've created a sheet for you here. If you just pay attention to what I've just shown earlier, no, it's not the correct sheet. This one here. This is what I've just shown earlier to you. This is your perceptron with 2 inputs, X1, X2. This is what you've seen in your truth table. Each of these inputs will have a corresponding weight, W1, W2, and you have a threshold theta. Yep. And as you can see here, this what I'm shading here is your training set, what I've shown you on the slide. So when it is 0, 0, you have 0, 0, 1, you get 0, 1, 0, you get 0, and 1, 1, you get 1. What I've done here, I've copied this many times because this is one epoch. This is the same data replicated many times so that you have 3rd epoch, 4th epoch, 5th epoch, and so on. Yep, I've done until 10 epoch. But typically when you do training in MATLAB or in Python, it's going to run for thousands of epochs. Yep, so it's going to be done iteratively. I'm using Excel here because you can very easily illustrate using Excel how the training is done. So this is called one epoch, as you can see. And in one epoch, you have 4 iterations. Yep. And then, of course, after the 4th iteration, you have 5th one, but you'll be going to 2nd epoch, and so on. Now, as I mentioned, this is your training data, and this is your desired value I've called Y. This is what you want. If in any process you want to use to train your neural network, you would always have a desired value, what you want. This is what you've collected. Now, what I'm going to get from the neuron here, Y, we call YA. Now, how I calculate YA, I've shown you earlier, you have to do activation. So how we do activation, I'm just going to insert a new column just to make it clearer for you. I'm just going to call that here. Yep, I'm just going to call that capital X. What was capital X? Earlier we mentioned capital X is simply the product of input with a corresponding weight. So I will take, now before we do that, sorry, you have the weight W1, W2 here, which I need to initialize some random values to start. It's just, you need just to give random values, typically between minus 0.5 and 0.5. It's typically then automatically when you use any software. I put here 0.5 minus 0.2. You could have put any other value you want. So these are initial values, can be randomly assigned. Same thing for the initial threshold theta. I'm just putting a value of 0.3, but this would be modified shortly so that I'm able to converge to some weights and threshold, but allow me to get my desired value. Yep. As we also mentioned, you have the factor alpha. Remember, if I go back to the slide, so if that was not very clear, I just want to show that back to you. Remember, you have you're taking product here. If I go to this one, you're taking the product of your input with your error. The error would simply be the difference between the desired value and the actual value. That's straightforward to calculate. The input is available from your neural network. Nothing difficult, but alpha here is a fraction which you typically choose between 0 and 1. We are using 0.2 in the sheet I'm about to show you, but you could modify that between 0 and 1 and see how it modifies. Yep. So let's try to implement that. Sorry, it's under 1. Okay. Now, first, I would want to first calculate capital X. Like I've shown you earlier, capital X is a weighted sum of inputs. So you take X1 times its weight, which I've given a value of 0.5, plus, because capital X is a weighted sum, X2 times W2. Yeah. So this is basically what your weighted sum is. In this case, it's 0 because it's 0 times 0.5 plus 0 times 0.5. Yep. What are you going to do next? I'm going to insert one more column. You always take capital X minus the threshold theta. I mentioned that earlier. You always take capital X minus theta. So let's do that. Is equal to capital X minus theta. I've given a value of 0.3. So these are the steps here. So first you do a weighted sum. Then you calculate X minus theta. Once you get to X minus theta, you're ready to activate the neuron. And since we're using a step activation function, like I've said earlier, you can use if. So if X minus theta is greater than or equal to 0, then the output is 1. Else it is 0. Remember, we said that earlier. I've shown you in the Excel sheet earlier. We can create the step activation function simply by using if. So if X minus theta, which I've created already, that is your J4 here, is greater than or equal to 0, then the output is 1, else it is 0. So this is my activation. I've activated my neuron. As expected, if it is negative, you should get an output of 0. Now, so far, I've been able to calculate an actual value Y, which is the output of a neuron here. This is what I've got, YA. Next step, you always have an error because this is what you want and this is what you're getting from the neural network. So you can calculate an error. So is equal to the desired value minus the actual value. Sorry, you get the error. So currently the error is 0. So I'm happy because if you look at the output of a neuron is 0, the output I want is also 0. So basically I will not modify anything, but we would write one equation and then we're just going to auto-populate the whole sheet to get the output. So what I've said earlier, if I just go back now to the slide, I just want to make sure you understand this. Remember how we modify the weight is by taking the product of the input with the error and then multiplying by the learning rate, which is 0.2 here. So I need to take the corresponding input times the error I'm getting. Let's do that. So the correction factor for weight W1, yep. So yeah, let me do that. Yeah, is equal to, so alpha is actually here, and I've programmed alpha in the sheet. Let's take 0.2 directly, which is 0.2 here. I'm not going to use any variable just to keep it simple. So it's equal to alpha times X. What is X for W1? It is X1. And where's X1? It is here. So it is alpha times X1 times the error. This is the error. So this is a correction factor which I'm going to apply. I add it to the previous weight to get the new weight. So I'm going to again explain that. Yeah. So I need to alpha X times E. So alpha is 0.2. I'm choosing an alpha 0.2 in this particular example times X. So X is nothing but X1 because I'm dealing with W1. So W1, the input is X1 multiplied by error. The error is here. It is 0 or not. I'm just clicking on this because when we go down, the error will no more be 0. Plus the previous weight to get the new weight. So this is the correction for weight W1. Correction for weight W2. So same thing. I need to take alpha, which is 0.2 times x. Of course, x for W2 is x2. So I will click on x2 times error. This is your error plus the previous weight is this one. I'm going to get here the new weight. Again, same thing as before because the output was the same what I want. I'm not going to correct. For the threshold fit test, it's a bit more complicated. Yep, maybe I will do that next week. I'm just going to write the equation for you here. It's very similar to what we're doing, but there's a bit of theory you have to cover. But I think we are out of time today, so I'll explain it next time. So it is equal to, again, alpha times -1 times the error plus the previous value of threshold is here. So what we've done here is one iteration. So this is one iteration. After one iteration, I'm correcting for W1, W2, and threshold. Why? Because this is what I've said to you. We typically correct the weight and the threshold to converge our neuron to achieve the desired output. So currently, I've just done one iteration. I need to feed the whole epoch. Now, how do I proceed the next epoch? I make this one. I take the weight here. Yeah, I bring it into the next iteration here. So this becomes the initial weight. So this would come here. This value would be the final one, would become the weight you would choose for the next iteration. Same thing for the threshold. So here you've been able to take the final values in the previous iteration, bring it into the new iteration to get the new values. And once you do that, you just have to auto-populate here. And then once you do that, you can just start dragging down. So it is auto-populating. This is how it is modifying. So it's taking this final weights, using initial weights, and then activating and doing that continuously. Let's look at our YA or the error. So at this point, you can find the error is not always 0. For example, let's look at this one. The actual output of the neuron is 1. I wanted to get 0. So my desired output was 0. I'm getting 1. So this is why the error is -1 because 0 minus 1, you get -1. Let's look at this one. The error is 1. So I wanted to get 1. My neuron is giving me 0. Now, why it is giving me 0? I've activated it. If I double click here, it is activating. Yep, I'm taking my weighted sum of input with the weights, subtract the trait data, and then activating it with a step function, and I'm getting this output of 1. Let's continue. So this is one epoch. Let's do one more epoch. Let's see what is happening to our error. So this is what we are saying. The error is still not 0. So it's not yet converged because you can see your error still have -1 and 1. Let's continue for the third epoch. Third epoch, we see the error now. You have, this is the third epoch from here to here. You can find you have 0, 0, but this is still -1 because I wanted to get 0 and the output is 1. So I'm getting -1. Let's keep going. Like I said, typically you would do hundreds of epochs. Let's see if this one converges. We expect it to converge because it's an n function which is linearly separable. The error is now 0. Can you see the error is completely 0 here? Let me do one more epoch and let's see what we get. Yep, the error now is constantly 0. If I just drag down, my neuron has converged. Yeah, if I just do until 10 epochs, you find that your error now is consistently 0. If you wanted, you could have plotted a graph of your error to see how it is changing. This can be done. Yeah, but you can see your error is constantly 0. If I come to the last epoch, let's say we take this one here. Your error is constantly 0. Why? I wanted to have 0. My neuron is giving me 0. I wanted to have 0. It's giving me 0, 0, 0. Yep. And I wanted to have 1, my neuron is giving me 1. Now, what do you do with this? This is what typically many students tell me. What do I do once I've reached at this stage? This is the intelligence. This is your weights and the threshold. So when you put W1 to 0.3, W2 to 0.2, and the threshold to 0.5, in this diagram here, your neuron, your perceptron is able to replicate the n function. This is what it is. Yep. So it means like as expected, remember when we drove a scatter plot for the n function, you are able to draw a straight line. So you expect the perceptron to be able to replicate the n function. And yes, we find that when we use a simple perceptron rule, which is alpha times x times e, it is automatically now modifying the weights as you do the iteration, ultimately to converge to an output YA, which is which is converging. Now, if you do the same thing for the Xor, remember we said the Xor is not, you can't converge for the Xor. Yep, I'm going to send a sheet to you. You can play around with it. Yep. If you do the same thing like I've done here for the Xor, you'll find even if you go for millions of epochs, it will never converge. Simply because the Xor, you can't draw a straight line between the classes. So this is the Xor here. If you look at the training set, yeah. So 0, 0, 0, 0, 1, you get 1, 1, 0, you get 1, and 1, 1, you get 0. I've just copied that many times for many epochs. So this one would typically need many epochs, and it will even not converge. So I would encourage you to just play around with that if you understood the concept I've described. We would pick up on that next time. And I will show you next time the MLP, the multi-layer perceptron, which can be used for the Xor. Yep, as we've seen, you can't draw a straight line for the Xor, so it will never converge as such. So I hope this one was clear to you. Unfortunately, I could not go in all the steps because that would need maybe a couple of hours to explain everything in detail. But I hope you'll be able to see how to mathematically model one neuron and how to make one neuron replicate something like this. But once you're able to do it in this way, there's no reason why, if I just go to slide last thing for today, I know it's a bit, you can even feed data like this, which is for x1, x2, this one could even be non-binary, like continuous numbers like this. You can make even this one learn on using a perceptron. Yep, I've taken a very simple example of a Boolean equation to explain the concept. But now if you understand this one, you can extend it to any classification problem where your x1, x2, even x100, a number of inputs could be fed into that. And typically you will use Python or TensorFlow or MATLAB to do the training. Yeah. Okay, this is where I would stop. I think we're going a bit above time. Sorry for that. But with this understanding here, I'm sure you'll be able to learn on your own. And if you can model one neuron, you can now extend and do very interesting things, especially what we do next week with MLP, where we start connecting. Just to show you how an MLP looks like, it looks like this. Yeah, this is what an MLP is, where now you understood one neuron. So if I give one neuron with many inputs to you, with many weights and threshold, you're able to calculate the output. So if you start connecting many neurons together, you should not have any problem to do the activation. But unfortunately, the training is not as simple as that. I will explain next time in broad lines, just to give you an indication. Yeah. So back to you, students, to continue.
Thank you, Dr. Gulchen, for this knowledgeable presentation. Now we will begin our question and answer session. So, how many questions can we ask you?
You can ask any. I'm happy to answer. Yeah, you can ask any more questions. That's fine. Let's get started and see where we go. Yeah, we can take some questions maybe next week as well, but I'm here to help you.
Okay, thank you, sir. The first question is, will AI replace human labor, and to what extent?
I don't think it will always replace human labor. If we are intelligent about AI, you see that we can use AI to do repetitive tasks, especially for tasks which have high data, like huge amount of data, which human beings are not good at interpreting. If I give you a big table of data, I ask you to do interpretation, it's difficult to do. Whereas a computer or AI algorithms are very good at that. So the way I see AI is really automating repetitive tasks and then allowing human beings now to get a summary of the data to actually take the final decision. This is how I see AI. So if we know how to make good use of AI, we can really do very nice, innovative work, even allow it to become the motor for driving jobs, very interesting jobs for people. So this is how we need to adapt. So if you find AI replacing people, people should be intelligent enough to use AI actually for their own benefit. This is how I see it. Yeah.
Thank you, sir. The second question is, in the context of managing outcomes under different parameters, is AI biased?
The issue of bias is always there. The problem is, remember, what we're dealing here are algorithms. Yep, we are dealing with algorithms. We are using mathematical models. Like today, I've shown you one very simple version of the perceptron learning rule. What I've shown to you is very simplistic, but it's a basis for you to learn more. Actually, mathematics will do that. You can always add new terms to this alpha x times e I've shown to you to make it converge quicker, or to add things like momentum term and so on. But what I've shown to you is a start of it. So now from here, you can learn more. So you always have bias. Bias comes in many ways, from your algorithm, the way you're tuning your weights, the initial weights you're choosing, and bias also come in your data set. If you choose data sets which are themselves biased, let's say, I'll give you one example. If let's say you are collecting data set of a process and the data you're collecting is really covering only certain variations of your input. So your training will bias automatically. So when you would actually use your train neural network to predict the output, it's going to be focused in that specific region of variation of your input. Now, there are many applications there in very many examples of bias in literature. For example, if you train to predict, let's say, the disease in certain category of people, let's say black people or white people, then you are already creating a bias in your data set for this population. So the bias will always be there. But like I'm saying, if we know about this bias and we are able to factor it in our data collection, you can minimize the effect of this bias. But if you want to do it on purpose, unfortunately, this is also risky. It depends on the developer. Yeah.
Thank you, Seb. Will AI become a greater threat to privacy and rights?
I think I answered this question last time. I think so. We are already seeing that in our own life with big companies like Google, Facebook. I think there were even some legal suits in the past against Facebook and now WhatsApp. So these people have already found that when they get data from people, they are able to create products or services which are more adapted to us and make us, I won't say make us become slaves, but really make us more attracted to these services, and we want to use them more and more. You would see that on Yahoo and Google everywhere. When you start browsing, they always give lots of adverts, which are things which you really want. So they are becoming very good at that. The question you should ask yourself, how come they know these things from you? So it means they are already, in a way, spying on you and taking lots of data from you. So this is where legal frameworks will become very important. Unfortunately, this trend is expected to go more and more because these people need data from you, their customers, if you want the source of money for them, they would want this data more and more. And you would even know that people are paid to take surveys now. There are such type of surveys where you are paid to take part in them because your input is so valuable for them to adapt their products and services. So I think, yes, over time, it's going to become an issue. Now it's up to us, the users, to know how to protect ourselves in terms of maybe we can put softwares into our own devices, or we can put restriction settings. But I think the legal framework at the level of government would also be very important to control all this. Yeah.
Okay,
yes, sorry to interrupt you, Darrell. Just informing you guys that we have already sent the registration link for your certificate of attendance, actually, because I know that it's a bit late and some of you have to leave us, so you can fill it. And for those who are still here, we can continue to take the question. We have one from Zishan in the comments, Darrell.
Yes. What resources can you recommend us to complete what we did today?
Okay, I would recommend, there are so many open source, so there are platforms like EDX, Coursera. I have myself learned from them. So I would highly recommend these courses. And these courses are not paid. So there are two options. One, you should pay to be able to get a certificate. You would know about that from Coursera or EDX. But it's a very useful resource if you want to get started. And if you read on the web, there's so much information out there. Unfortunately, from my personal experience, I think if you get started straight away into learning about AI, it can be a bit difficult depending on how the information is presented. It can be quite abstract. This was the whole purpose of that session we're having with the free pass, to get you really started on the fundamentals. We started with AI, the debate is going on. And today, hopefully, you have been able to grasp the way you can mathematically model one neuron. And the next session will be on NLP. I think if you get these components, even the fundamentals of them clear, when you go into now following these courses on EDX or Coursera, you'll be well placed now to build up the competence. So I would suggest these online courses. If you can afford to pay $50, for example, then you actually can send assignments and they will correct and give you a certificate. So that's something very interesting. In $50, around 2,500 rupees, so not that much. You can have a quite good knowledge. But if ever that's difficult, you can always follow this course, but not pay anything. But then you won't get a certificate, but you would have access to all the contents. Yeah.
Okay, sir. We are having more questions coming. I will take one from Niman Hemkesh. How many errors must be equal to 0 before we can confirm with the next data generated? We are confident, sir.
Yeah. So like we've seen today, when you will do training, you will never get, this is something called recognition accuracy when you talk of classification. The example I've shown to you was 100% because it was very simple, it was just 4 data set. But typically when you take real life examples, you will not normally get 100% recognition, means not all your output would be the desired value. You will get some data which will not be exactly the same as perfectly normal. This is what we talk about recognition accuracy. Let's say you get the recognition accuracy of 80% or 90%, then it's up to you to assess for the application you're developing. Is it good enough? Because like I mentioned, human beings themselves are not perfect. If you give a task to a human being, the human being may do mistakes. So we should not expect these algorithms to be 100%. If you get 80%, I'll give you one example. Let's say you want to develop a software for the police to recognize criminals. So you have taken the picture of a person, you're matching against databases to see if it is corresponding to a criminal. Let's say the recognition accuracy is 80%. What this means, the police would have an 80% chance of actually finding the person, and then it's up to them to take over. So it's always there that the human being would be actually supervised. The danger would be if we are expecting the system to be fully autonomous. Then you would need to be careful what sort of output is being given and how far can you rely on the system only to make decisions. So if you have fully autonomous, unsupervised system, then you have to be very careful. But if you're coming to system to assist a human being, to guide him, another one, let's say you are developing an application to detect fractures in the bone of X-ray images. So doctors would be guided by the image. Let's say it is 75% or 80% accurate. The doctor would be guided to the screen and say, yes, there's an 80% chance of a fracture there. The doctor is going to be complemented and then really look at it and then take a decision. So in that sense, it's not a dangerous system. Like I'm saying, even doctors can miss a fracture. So why should we say the machine should have 100%? Yeah.
Okay, thank you, sir. We have another question.
Yeah.
What skills are required in the involvement of AI research? And I think this question is also for the mechatronics student because for now I am in year 1 and interested to hear about it.
Yeah, definitely. I think there's huge scope, like I've said, for mechatronics especially, it's a huge scope because I'm myself from a mechatronics background, but like I was saying, there's something in it for everyone because you'll be using AI everywhere. Now, what sort of skills would you need to be able to use AI for developing AI or for using AI? So when you look at the field of AI, you have 2 broad categories. One category of people will be the developers of AI algorithms, the software itself. And one category will be people who's going to use it as an application software, application development. So myself, I'm more on the application type. So I use MATLAB, I use Python to develop applications. If I got data, I'm going to try to develop it for research. Whereas people from computer scientists or from mathematical background, they'll be more interested about algorithms to optimize. We're going to talk a bit about that next week when we talk about MLP. We have a huge contribution of mathematicians, mathematical frameworks of optimization there because you want, like we discussed today, you are trying to fine-tune the weights and the threshold of one neuron. But imagine if you have thousands or millions of neurons to train. Now you have a problem where you have thousands or millions of weights to adapt and it becomes a very complex mathematical problem to solve. So it is about mathematicians now to really, they have developed algorithms to allow us to optimize this multidimensional space where you have lots of thresholds and lots of weights. So you have inputs of mathematicians, you have inputs of computer scientists, of software developers to create these GUIs for us. Now, on the application side, then it is unlimited. People from finance, from economics, from agriculture, from robotics. So it depends how you're getting your data set and what sort of applications you have, even for electronics, IoT people to collect data, data science people to make sense of the data. And you have embedded control there, you have microcontrollers to actually deploy these systems, these algorithms in a system for it to be applied. So I think it is here for everyone. I would say clearly, but like I hope I've given you some indication. Basically, it's about software development, computer programming, mathematical algorithms, but also about system design and also integrating the solutions in these systems, which typically mathematicians or computer people would not do normally. They were going to be interested in a computer environment, but we are interested to deploy it outside the real world. Let's say you're talking of an agricultural system. It has to be on the field and working. This is where engineers will be involved. So I think it is in for everyone, but basically mathematics, computer programming, and then you have IoT sensing. You do have a huge part about sensors, actuators, which mechatronics would be very much involved in. And I think everyone can get into it. And if you're talking about algorithms here on the computer, then like I mentioned, economics, finance people, everyone is going to be involved in it. Yeah. Just maybe to add something, if you want to really become good at AI, I would encourage you to really get into the mathematics of it. Today, I've gone a bit into it. I hope it was not too overwhelming for you. This is really the start of it. But if you want to become good at AI, I would encourage you to also go into the mathematics of it. So when you're getting the output from the neural network, you know what's happening. You're not just using it as a black box. It can be quite dangerous. Yeah.
Okay, thank you, sir. I think it will be very interesting for us later.
Yes, you do have modules coming up, but like I said, if you're interested, you should read more about this. There are lots of examples, lots of resources online to learn on your own. And like I mentioned, there are lots of online courses from EDX, from Coursera, which start from very basic level and teach you. Typically, they will teach Python to you. So I would encourage you to learn Python programming if you don't have that as part of your program. Python is a software which is used increasingly for AI now, because you have libraries having written, and so you don't need to start from scratch. You can just apply the libraries, the functions to just solve problems quickly. So I would encourage you to learn Python.
Okay, thank you, sir. Can we proceed with more questions?
Yes, I'm fine. Yeah.
Okay, thank you, sir. How efficient, can AI algorithm be, and how does the efficiency affect the decision-making process?
Yeah, so when you read more about AI, you're going to see there are some metrics which you would come across. Like for any system, let's say you have a motor, you would talk about efficiency. Any process you would have some performance like KPIs, which you would have to assess how good your system is. So when you come to neural network, you have things like false prediction or true prediction, which unfortunately we can't cover. But when you go in more detail, you have some metrics there to assess how good the neural network was in predicting the good values, but also the negative values. There are things like false positive and false negative, true positive, true negative. So this may be a bit mind-boggling. So the true positive means it was positive, and the neural network has said yes, it is positive. A false positive, it means the neural network is saying it is positive, but it was actually negative. And then you have true negative and false negative. If you have these 4 parameters, you can start calculating things like recall, accuracy, and so on. So based on that, you can assess. But down the line, like I've said to you, you will never get a system which is 100% efficient, because you will always have some combinations of inputs which the network has not seen during training. This is where the adaptation comes. Remember, I mentioned last week, your neural network should be able to adapt to situations it has never seen. This is where the intelligence comes in. We also human beings, when you will be one day as engineers, you'll be confronted with problems you've never solved before. So how do you adapt to the situation to propose a solution is going to showcase your own intuition, your own expertise, but it has uncertainty as well. It may fail. So this is where the challenge lies. So you should not expect neural network to be 100%, but when they will do a mistake, you can learn from the mistake. Let's call reinforcement learning. You can now take this mistake you've done to train the network again. It's not just one training is finished. You can have ongoing learning like we human beings do. So when your network has provided an output which you are not happy, you can integrate that as part of a training and train the system again. And next time it's going to be better and better. This is what I mentioned in the first part we've covered about these games, this computer system which play chess or play Go. So initially they are not good, they do lots of mistakes. But if you allow the computer, because the computer not like human beings, they can learn 24 hours, even days they can run. You can just leave it to them and they're going to learn. And they become so good at it, then they will stop doing mistake at all. This is how they're beating the world champions in chess or Go. So this is called reinforcement learning. You do mistake and then you lose a mistake to correct yourself. You correct like this, ultimately you become expert. So computers all learn like this actually. Yeah.
Okay, thank you. We'll continue with another question.
Yeah.
How long will it take for AIs to learn new data sets?
New data set, you mean that question is a bit generic. I would say what you mean by new data set, maybe it means a network has been trained already and you're adding more data to it, or in terms of you're taking new data set and you're learning from scratch. It depends how complex your network is. If you have a small number of neurons, like I've shown you in Excel, it took only a couple of minutes for the network to Perceptron to converge and to give me the end function. Just few iterations. But as we'll be seeing next week, when you come to network which are connected neurons together, where one weight would influence the other one, it becomes quite difficult. It may take days for a network to run, to converge. From my personal experience, it can take 3 to 4 hours on a good computer. If you have large data set, it can even take weeks sometimes. It depends on the complexity of the problem. Yeah.
Okay, thank you, sir. So we will entertain one more question. Is it possible to use the mathematical model to find ways to enhance the speed in re-educating of limbs for medical purposes?
Yeah. So actually, there was a project I've worked in the past where we use robotic system. Let's say someone had an accident. And this is what is a plasticity of the brain. Remember when we talked last week, we mentioned about our neural network of plastic means it's not static, it's going to continuously learn. Let's say a person by birth or maybe had an accident and part of the brain has been impaired, and that brain corresponds to the gait, means how we walk. So what we can do now, we can use robotic system to attach to the limb of a person, and we can program the actuators to make the required gait of a person. Yeah, how it's going to work. Now, the fact that now this person's limb are moving, this gate is going to be programmed inside the neuron, and the person can learn again. So this is what the plastic behavior of the brain is. This is used a lot as part of rehabilitation. So robotic systems have been designed. If you just Google on that, there's one special disease called cerebral palsy. Yeah, cerebral palsy. This is what we're talking about. So it may be from birth or as a result of an accident where the person maybe loses the notion of gait. Yep. So using robotic system now attached to the limb and to the hand, you can make the person walk on a treadmill, and by making these movements here, the brain will start recollecting these specific gait. And like we mentioned today, these weights and threshold in your neural network will be learned again. Over time, the person can start walking again. Yes.
Okay, thank you, Dr. Gouchen. Thank you very much, Dr. Gouchen, for answering all the questions.
Thank you.
Thank you for attending this session. The link for the attendance sheet is posted in the chat box. Please note that at the end of a 3-day workshop, we will be awarded a certificate of attendance provided that you attended all 3 sessions. And it is with a great pleasure that I invite you to the last session of the workshop, which will be held on the 9th August at 7 p.m. Don't worry if you miss some part of the webinar. The recording will be uploaded on the Engineering Community's YouTube channel. Before ending, we want to express our gratitude to Dr. Gouchen for his time and very detailed presentation. Thank you to everyone who attended this session. A webinar is not fruitful without his audience. I want to thank the iMakers Society for giving me the opportunity today. And also, personally, I want to say that years ago, I would never imagine myself being here with you it's a immense honor for me to be the host today. Thank you and have a nice evening.
Thank you, everyone. Good night.
Yes, merci beaucoup. Bon, sais-tu que je trouve ça session un petit peu intéressant qui premier là, moi c'est vrai que troisième là encore plus intéressant. Et ça fait je vous me trouve que maintenant il y a une question qui n'est pas réussi à répondre. Can we sue a company for collecting our data? Peut-être capable de prendre les quickly parce que
Oui,
les
bien
sessions
sûr, il y a un Data Protection Act qui un civil case, hein, je ne peux pas prendre les données sans nous permission. Il y a un Data Protection Act, je ne peux pas prendre les données sans nous permission, mais c'est moi quand nous rentrons devant un website, quand nous mettons, par exemple, nous faisons un search, nous mettons un keyword, tout ça là, ça, généralement, je suis capable de prendre, mais c'est moi un data personnel, de ne pas y avoir. Bon, ça veut dire s'il y a un cas qui est trouvé, qui prend un data personnel et c'est venu pour un but, je suis capable de poursuivre.
Yes, okay. Yeah, tu sais, derniers temps, il y a beaucoup de concerns on the privacy of data. Yeah, et sais-tu que, enfin, l'étudiant qui nous pose cette question, il est un telecommunication engineer, donc, yeah, because networking, everything centered towards you currently, guys. Donc, moi aussi, je ne vais pas trop tarder aujourd'hui pour quitter. Merci beaucoup encore, Promotion, pour avoir aimé tout cette visite-là. And yeah, cannot wait for the first session actually.
Allez, bye bye.
Merci beaucoup, goodbye.
Bye.